Consider you have a simple pendulum. So I'm gonna put a simple pendulum and I'm gonna suspend it. Oops. So a simple pendulum of mass m is suspended by a massless inextensible string of length L. And we're gonna go ahead and put a basis here. I'm gonna put a polar basis, so ER points like this. To figure out how E theta is gonna point, I have to draw the fixed basis EX and EY. So for example, if I draw EX and EY like this, then theta is this angle. From EX to EY, that's the angle theta, and E theta is such that ER cross E theta, which is EZ, is equal to EX crossed with EY. Very well. So we set up our bases here. Now if I want to draw the free body diagram of the mass, the forces acting on it are the weight force, that's gravity acting this way, the weight force and the tension force. The weight force acts in the same direction as gravity, so weight is mgex, and the tension force acts along the spring, so it's acting along minus ER, minus T ER, where here T is positive. Now, how do I show, or how do I answer the question, is the linear momentum of the pendulum conserved? Well, let's remember, what's linear momentum? Linear momentum is this quantity g, which is equal to mv. That's the linear momentum of a particle. It's its mass times its velocity. And we have the balance of linear momentum equation, which is F is equal to g dot F is equal to ma, if m is constant. So how do I show that g is a constant? Well, if g is a constant, conserved, meaning that it's conserved, then we need F is equal to 0. The sum of forces acting on the particle is equal to 0. And that's not the case. Here, the tension force plus the weight force, they do not sum to 0. The acceleration of the particle is non-zero, so no, linear momentum of the mass is not conserved. G is not conserved. Now, what about the angular momentum of the mass? Is the angular momentum of the pendulum or of the mass conserved? Well, what is angular momentum? Well, and let me fix this question. Is it conserved about O? Where O is the origin here. Always when we talk about angular momentum and sum of moments, we always need to specify which point we're talking about. So is the angular momentum, which is HO, the angular momentum about O, is it conserved? HO, remember, the angular momentum is equal to R cross mv. And remember the balance of angular momentum equation, the sum of moments about a fixed point O is the rate of change of the angular momentum about O. So if HO is constant, or for it to be conserved, we need the sum of moments about O, then, and vice versa, the sum of moments about O is equal to 0. So to show that the angular momentum about O is conserved, we need to show that the sum of moments about O is equal to 0. And if that's not the case, if the sum of moments about O is not equal to 0, then the angular momentum of the system is not conserved. Okay? So here, I will need to calculate the sum of moments about O. The sum of moments about O. Well, how do I calculate the sum of moments about O? It's the sum of moments about O is the position vector from O to the point of application of the forces, so this one, R, crossed with the forces. Remember, both forces are being applied at the particle. Weight and tension is being applied at the particle. So the position vector from O to the point of application of the forces is the same as R, the position vector to the particle, and the forces are the weight and the tension, whose expressions we've written over here. So MO is equal to R cross F, which is R cross the tension minus TER. And I'll write the expression of R in polar coordinates. That's equal to RER cross minus TER plus MGEX. Now I'll distribute my cross product. That's RER cross minus TER plus RER cross MGEX. Now here ER cross ER, that's equal to 0. The first term is 0. The second term involves the cross product of ER and EX. So I'll need to either write ER in the EX EY basis or EX in the ER E theta basis. Here I'll just write ER as cosine theta EX plus sine theta EY cross MGEX. So the EX cross EX term is equal to 0, but the EY cross EX term is equal to minus EZ. So then MO is gonna be equal to RMG minus sine theta EZ. That's the sum of moments about O. It's different than 0, so HO is not conserved. Okay, how do we actually calculate the angular momentum of the system? HO, remember, is R cross MV. In polar coordinates, the position vector can be expressed as RER, and the velocity is R dot ER plus R theta dot E theta. Here we will remember that R dot is equal to 0 because R is equal to the length of the chord, which is constant. The chord is inextensible. So I'll write this calculation as LER crossed with L theta dot E theta, and that's equal to L squared theta dot ER cross E theta is equal to EZ. I think I forgot my mass term. I will add it, and that's the sum, the angular momentum, of the system about point O. So again, how do I show that the linear momentum of a system is conserved? The linear momentum of the system is conserved if the sum of moments, if the sum of forces is equal to 0. The angular momentum is conserved if the sum of moments about O is equal to 0. Now energy is a little bit different. How do I show if the energy of a system is conserved? How do I show? So is the energy of the mass conserved? Okay, remember that the energy of a system is conserved if all the forces doing work on the system are conservative. This is equivalent to saying that all the non-conservative forces are workless. So if I draw my free body diagram again of the mass, I have the tension and the weight force acting on it. The weight is conservative. The tension here is non-conservative. So for the energy of the system to be conserved, I'll need the tension force to be workless. Is the tension force workless? I'll have to calculate its work to figure that out. So to calculate the work of the tension force, I'll have to integrate the tension force started with the velocity dt, which is equal to minus TER, and the velocity is R theta dot or L theta dot E theta dt, which is indeed 0. The integral of 0 is 0. So the tension force is workless. Hence, all the work of all the non-conservative forces is 0. So yes, the energy of the system is conserved. Yes, the energy of the system is conserved. So finally, we have a conserved quantity here. For a pendulum, the linear momentum is not conserved. The angular momentum is not conserved, but the energy is conserved. And this conservation of energy allows us to solve some problems. For example, if I have a pendulum that's released from rest in a certain configuration, I can find the maximum velocity attained by the pendulum, and that's going to happen at this location when the angle theta is equal to 0. Oops. My pen is a bit stuck, so we'll review this, we'll continue this example in another video.